¿Sí? Vale. Soy Rafael Lainez de Azken Muga, o en estas latitudes es Azken. En el norte nos conocen como Azken. Somos proveedores de soluciones gráficas de hace 20 años, 21 años, y relacionado con las gráficas hemos estado siempre vinculados a fabricantes de tecnologías gráficas. Y bueno, no quiero quitaros mucho tiempo porque sé que las ponencias son, la norma es que sean en español, pero no quería perder la oportunidad de traeros un arquitecto de soluciones de NVIDIA con un currículum potentísimo en Machine Learning, con 12 patentes de software, y que se llama Adam, de apellido impronunciable, Grzywaczewski, creo que se pronuncia. Y creo que es una ponencia interesantísima para que veáis más o menos cuáles son las claves de Deep Learning, dónde se puede aplicar, qué viabilidad tiene y luego qué requerimientos computacionales tenemos. Es un poco, no es muy técnica, porque él ha hecho un gran esfuerzo para resumirnos un poco, para que no sea una pesadez técnica, ¿no? Y os dejo ya con él porque no le quiero quitar tiempo, la ponencia me parece muy interesante. Estamos fuera para luego, hasta el final del evento, si queréis resolver cualquier tipo de duda. Hay personal de NVIDIA, como Marc Domenech, yo o el propio Adam, pero tiene que ser en inglés. ¿De acuerdo? Pues gracias.
Hello everyone, can you hear me?
Yes.
Perfect. Let's try to turn it on and let's pray that it actually works. So how much time do we have? Perfect. I'll hold on to that. So, and the clicker works as well, great. So pleasure to be here. My Spanish is rubbish. I've spent a couple of years in Barcelona, but I prefer not to. So I do machine learning. For the last 10 years I've been doing machine learning for quite a lot of people. Right now I'm working at NVIDIA as a deep learning solution architect. What it means that I go to companies like the ones that you work in and I help them build their AI products. Rather than trying to explain what I do, I have a short video, less than 2 minutes, showing what we've helped other companies build. Let's have a quick look, and that will set a scene for the rest of the presentation.
I am a visionary, exploring a universe of data to sharpen our view of the most distant galaxies, and studying black holes to help prove Einstein's theory of gravitational waves. I am a healer, giving doctors the power to turn mountains of data into life-saving breakthroughs, identifying diseases like leukemia from a simple drop of blood, even in our own homes, and finding new ways to bring cures to market faster. I am a protector, keeping our oceans safe from invasive species, and helping our crops flourish while minimizing pesticides. I am a helper, assisting customers in stores and the disabled in their homes. I am a navigator, mapping our world 1 millimeter at a time, and making even the largest self-driving vehicles safer for the long haul. I am a creator, learning to paint from the masters and applying their styles to create original works of art. I am a teacher, analyzing 500,000 player moves every game to identify strengths and weaknesses, and a learner, discovering new strategies from complex games. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
So yes, so what strikes people is the fact that there are so many different applications. So we saw everything here, from designing medicine, from protecting the seabeds, from analyzing video for hockey player moves, to composing music, which is my personal favorite. But how do you choose your own application? So how do you assess at the early stage what is possible and what is not? Especially that you hear those quotes quite frequently. So Andrew Ng, who is the founder of Google Brain and actually one of the key fathers of modern machine learning, said that AI is the new electricity. So similarly to electricity, which transformed our world 100 years ago, he believes that artificial intelligence will transform literally every single industry in the next several years. So how to evaluate what is possible and what is not? And this is what I want to give you today. I want to give you a bunch of heuristics, very simple rules that you as business owners, product managers can apply at the very early stage to get an initial idea of what is today possible and what is most likely still within the realm of fundamental research. And secondly, I want to share with you some how to get started. So what you need in practice to build your own solutions. So let's get going. So what makes AI projects successful? The type of a project you choose. So currently, majority of problems that are applied and that bring commercial success fall into the supervised learning category. And actually all of the problems that you saw in the video were supervised learning problems. So the tractor was scanning the soil, so the input data was the picture of the soil with plants, and the labels were just annotations on the picture saying this is a plant of lettuce and this is a pesticide. Similarly, when you look at sea floor exploration, you had pictures of the seabed, and someone actually had to create the labels with annotations of different plants. And actually, that's actually not that constraining. There is a huge range of problems that fall into this category, and those are just a couple of examples that you know from your daily life. So images, names of objects in images, so Facebook, pictures of faces, and then names of people in the pictures. Speech and then text, so your phone, Siri systems, etc., etc. Those are all deep learning artificial intelligence systems. Video, so our football or hockey game, and then event statistics, so number of football or hockey passes. Mortgage application, and then mortgage risk assessment. Text, speech, English, French, German, Spanish. Click-through data, content recommendation. Those are all supervised learning problems. And if you have a supervised learning problem, that's a good start. Not all of the supervised learning problems are really that suitable for deep learning. Some problems are still better suited with traditional machine learning algorithms, and that's a really good heuristic from Ian Goodfellow, so the father of generative adversarial models, which are, as Jan LeCun said, the biggest hope, the biggest development of artificial intelligence in the last 40 years. So if you have a problem that has a lot of noise and very little structure, then most probably this is not the best candidate for artificial neural networks. If you have a problem with little noise and very complex structure, then most probably yes. And there are a lot of problems with complex structures. Speech is a problem with extremely complex structure. So you have phonemes, then you have words, then you have sentences, then you have abstract meaning. Those are all different components of a structure. Images have huge amount of structure, so pixels, edges, noses, ears, heads, people, dogs, cats, that's all part of the structure. So if you have a problem that falls into this category, then most probably that's a good candidate for you. But what type of a problem is it? So a lot of people ask that question, and they don't only ask that question to myself, but Andrew Ng, who was working at the time at Baidu, he had a team of product managers, so people that were personally responsible for individual pieces of functionality that they would sell or provide to customers for free. And they didn't know how to evaluate what is possible and what is not. So after a good couple of months of trying to figure out a good way to explain to them how they can evaluate the feasibility themselves, he came back with this heuristic. And I do appreciate that it's just a heuristic. It might not work all the time, but I think it's a very, very strong one. So let's read it. If a typical person can do a mental task with less than 1 second of thought, so overwhelming majority of our day-to-day problems, we can probably automate it using AI now or in a very near future. So think about it. If you see a picture of a lettuce, you know it's a lettuce. If you hear a sentence in English and you know English, you understand that sentence. Those are all problems that you do with 1 second of thought or less. Driving a car, you sit in front of a steering wheel, you know immediately what to do. But do you have enough data? And that's a quote from Brian Catanzano, so another gentleman from Andrew Ng's laboratory. Without a large data set, deep learning isn't likely to succeed. And I would like to stress that. So you need substantial amounts of data. And the formal term is inefficient learners. Neural networks are still inefficient learners. When we as human beings, we see a training example, we can learn from that single training example, building on years and years of our experience. Neural networks are not necessarily good with that. Saying that, there are some approaches already that are showing promise, so transfer learning, so you can transfer learning from one data set to another, but they are still part of fundamental research, and I show a couple of quotes in a second. And the key thing is the word labeled. So you don't only need the data. The fact that you need the labeled data is currently the Achilles heel of deep learning. So sometimes getting labels is really difficult. So getting someone to decide what actually right constitutes can be really hard. So if I would show to you a picture of a breast tumor, how many of you would know that it contains a breast tumor? Most probably no one, or very few of you. So you need to get someone that will be able to make that decision, and it turns out that doctors are great at finding those tumors, but they are not always 100% right. There are a lot of gray, difficult cases. So getting those labels can be really hard sometimes, so it's better to choose problems when it's easier to get those labels. And if the data set requires skilled labor to produce, that significantly limits scale and affects the cost. So think about it. If you need 20 doctors for 10 months to label your data set, that might be prohibitive for your budget. Saying that, if you need 500 just normal people, students, for 2 years, you can pay for that any time of the day. And heuristics again, because that was semi-meaningless in a sense, because it didn't give you any rational context. So this is another quote from Ian Goodfellow and Joshua Bengio, who is one of the fathers of modern neural network research. As of 2016, you need approximately 5,000 labeled examples per category. This is a heuristic, but it's a fairly decent one. That can be a good starting point. And in order to exceed human performance, you need approximately 10 million labeled examples. That is not beyond reach. You just with a bunch of students, if your problem allows for it, you can do that in a couple of weeks, months. Working successfully with data sets smaller than this is an important, and I stress this, research area. Yes. So if you're trying to tackle a problem where you do not have those labeled examples, it's definitely possible, but you should expect much more fundamental research that will have to go into that. So yes, so you've established a problem. You've identified this is what we want to do. This is the challenge that we have, and it falls into those categories. What to do next? In my opinion, and actually this is also part of Ian Goodfellow's methodology, one of the first things you should do is decide how you will measure accuracy, and you should do it day one. Decide what success will actually mean. and drive that success through accuracy calculation. Drive that success through dataset creation. So if you have product owners or managers responsible for delivery, rather than forcing them to create lengthy requirements documents, get them to create the dataset on which this accuracy will be tested. So if you're building a speech recognition system that needs to work in a loud factory setting, for example, ask your product managers to collect, I don't know, 500 hours of audio recordings in this particular factory where you have the same level of noise. That will drive requirements much better than any requirement document. And also think about unavoidable failure, because those are all probabilistic systems, so they will fail occasionally. So build defensive mechanism from day one. If your system is safety critical, think about how you're going to tackle those rare events or frequent events, depending on your problem, when your system will give you wrong prediction. And then, once you've established what your accuracy is, immediately build an end-to-end pipeline. And I'm not talking about building an entire product. You don't have to build fancy, flashy user interfaces and have everything integrated from day one. But what you should have from the very, very first moment is an ability to execute the machine learning pipeline and get that measure of accuracy. But don't do it with deep learning. Use a different, much simpler model on the first day. And that model is frequently referred to as default baseline model. So choose a machine learning model that your teams know really well. It doesn't really matter what it is. As long as they can tune it, they understand it, and they can push it to its limit, that's a really good candidate. So if your team has a lot of experience with random forests, use random forests. If they are good with boosted trees, use boosted trees. Build the end-to-end pipeline to calculate, to see how your system behaves from day one, and use something very simple, because it might as well work. You really never know with those things. And systematically measure your target accuracy, and also try to capture what is the level of human accuracy. Because not all of the problems have very tangible solutions. If I ask you to predict whether I'll like a piece of music or not, you will most probably not succeed. Even if I ask my best friend to evaluate that, he will succeed very frequently, but he will still not succeed all the time. So if humans don't get 100% accuracy, why should you expect machines to do that? So it's always good to have this benchmark somewhere on your report showing this is what humans can do, and try to strive to it. At least you'll have very tangible measures of success. So in terms of heuristics, that's more or less it. If you follow those guidelines, you will choose a project which is most probably quite feasible, and you'll establish very good working practice that will help you measure the progression of your team. But what do you need? What do you need to put in place in order to build solutions like that? And the answer is that depends on which stage. So this is a quick and dirty slide that I've put together to explain what I mean by different stages of machine learning or deep learning product development. You kind of start locally. You start on your desktop machine, which will have a couple GPUs, maybe 2, maybe 4, which sits underneath your desk. And this is the point of time where you're really building a prototype model. You're trying to figure out what works. You're experimenting on small data sets. You have to iterate very quickly. You make a lot of mistakes. But this is not something that will allow you to create product in majority of cases, because this will not allow you to train on large data sets. So once you're happy with the results of this stage, you usually need to move to much larger cluster of machines, or at least a bigger machine, where you iterate on the entire data set. And then there are a couple other stages that relate to putting your model into the production. Today I'll focus exclusively on this stage, A, because we don't have enough time, B, because this stage is very well defined, whereas those stages are very, very problem specific, so it would be a very difficult and long conversation. So I will focus on a stage where once you have a candidate model, you're trying to train it and iterate over it using the real data set. So one of the few things that you really, really need is compute. And you need really a lot of compute. And that's not an exaggeration. So this graph shows you basically the winners of the ImageNet competition for the last couple of years. So ImageNet competition is the competition, it was mentioned on the previous presentation, I think. It's a competition where algorithms are being benchmarked on a certain set of pictures, a couple billions of them actually. Inception 4, at the time of writing of this paper, was the winner of that competition, and it had a mind-boggling 50 million parameters. So 50 million floating point numbers went into the model. Think about an equation with 50 million variables or 50 million parameters. It's huge. And to take a single picture and push it through that network required about 17 giga operations per image, per forward pass. That's great, but how to interpret that? So another example, which is much easily digestible. So if you look, for example, at Baidu's deep speech model, so this model that they use in phones to kind of translate human speech into text and get the search queries, it was trained on 9,400 hours of audio recording just for English, and required tens of exaflops per a single iteration cycle. Bear in mind that your research team needs to go through that cycle hundreds of times. They need to make mistakes, learn from those mistakes, and start again. So they need to iterate quickly. So if you would train that model on a single GPU, it would take about 3 to 6 weeks. That's prohibitive. You cannot expect your team to wait 3 to 6 weeks for results. You're not paying them n hundreds, thousands of pounds or euros to sit for 6 weeks in between iterations. If it was a single CPU, the number would be even more mind-boggling, because those wouldn't be 3 to 6 weeks, it would be 3 to 12 months. So you need a lot of compute. That is why a lot of successful teams have a very mixed skill set. So what you'll see a mixture of machine learning and some level of HPC knowledge in those teams. And those models are not even big. So if you look at the biggest model for the image recognition, VGG, with 150 million parameters, have a look how it compares to Google language model. So this is the VGG network, and this is the model that Google is deploying right now for some of their language problems. It's 137 billion parameters or something. It's enormous. But there is a good reason why those models are increasing. And this is another curve that I borrowed from Andrew Ng. It turns out that classical machine learning models, when you provide them with more data, they increase in performance. But at some point, the increase in performance plateaus. It starts to stagnate. And historically, the only way of moving this curve up was through hand engineering of better features. It turns out that neural networks suffer from the same behavior. So given a certain neural network, its performance will increase and start plateauing. But what is interesting, you can move this curve upwards by just increasing the model size. So by increasing the model size, you're forcing it into a regime where it can actually benefit significantly from more data you give it. That is why the more data you have, and I have a good quote for it, Geoffrey Hinton is the grandfather of neural networks, and that's a quote from one of his presentations. For any size of the data, it's a good idea to always make the data look small by using a huge model. So if you have a tremendous amount of data, that's amazing. Just build a model that is drastically bigger than that. But it seems to have very good rationale. So evolution is one of those beautiful mechanisms that is very cost effective. If something is not needed, it's being killed. And if you look how our brains evolved, we have 10 to the power of 14 parameters as connections. But we only live for 10 to the power of 9 seconds. So our model is drastically bigger than the data set that we'll ever see, by a couple orders of magnitude, actually 5. So it makes always a lot of sense to make your data look tiny in comparison to a huge model, and that is being confirmed empirically. So this plot shows you how accuracy of certain family of models increases with the model size. You can see clear relationship. Yeah, 5 minutes, fully appreciate that, almost there. And that's not just an academic talk, we see it in production as well. So basically this is the evolution of models that you see in production across different companies. You need CPU as well, especially if your workload involves something like reinforcement learning where you have a lot of simulation. You need a lot of CPU just to feed the GPUs. GPUs can compute so much that it's very frequently a challenge to move the data in. You need a lot of RAM, because as those models increase in size, you have much more footprint in the GPU. There are things that are being done to address that, but it doesn't change the trend. So we are working very intensively on half precision training, so using 16-bit floating point numbers, but it doesn't change the fact that the models will increase in the future, and already significant amount of models are bigger than the memory of a single GPU. Which drives the need also for between GPU communication. So if your model doesn't fit into a single GPU, it needs to be spread across, and as a consequence, a lot of data needs to travel from one GPU to another. Similarly, if you want to speed up your training, you can train your model on multiple GPUs, but it has significant network implications as well. To give you an example, this is the Google translation model. You can see that not only doesn't fit on 1, 2, 3 GPUs, but it also doesn't fit on 8. And this is just a single neural network. Why am I mentioning it? Because the choice of your between GPU technology actually matters significantly. So even if you don't want to go with a technology that was designed for the AI use case, so we've built our own bus called NVLink, think about your PCI Express architecture, because the choices, architectural choices that you make when choosing them have also non-trivial impact on the amount of bandwidth that you'll get from a GPU. So it makes a difference whether you're connecting using 2 CPUs, using a QPI bus, or whether you have a dedicated PCI Express switch. So as I said, another reason why communication is important is because in a lot of cases, waiting 3 to 6 weeks for results is unacceptable. So what a lot of people do, they will use algorithms such as synchronous stochastic gradient descent to speed it up. They will have the same model trained on multiple GPUs, and every mini batch, so every set of samples, those models will synchronize parameters, and this drives not only between GPU communication, but also between computer communication if you're scaling beyond 8 GPUs. And this graph shows you, even for those simple image models, how much is being shuffled between nodes. Therefore, between node communication is also critical for your success. This graph shows you how the performance of training increases as you add network adapters, in this case InfiniBand adapters. So you can see that you can significantly benefit from 4 network adapters. Network technology is not everything. Implementing communication in a way that will be able to fully utilize the network bandwidth available is non-trivial either. So you can see differences in bandwidth achieved with 3 different communication libraries: NPI, Baidu All-Reduce, and NVIDIA's Nickel library on a machine with this network configuration, and its impact on the training performance. You can see that with Nickel you get near theoretical performance, whereas with NPI it suffers as you increase number of GPUs to 32. Storage is important, extremely important, because it needs to keep up with GPUs in your cluster. And you need a lot of storage for some of those problems, if you look just at the number of examples. So aim to have at least 200 megabytes per second per GPU. So usually 10 gigabytes per second will not cut it. This is a theoretical configuration that we would recommend for this type of workload. So 2 high-end CPUs, 8 high-end GPUs, half a terabyte or terabyte of RAM, NVLink bus between GPUs, couple InfiniBand adapters, preferably 4, and a lot of power. So if you want a very dense configuration with 10 units per rack, 32 kilowatts is something that you might need to consider. Otherwise, you might have to drop to just 4. And a lot of people do that. In terms of networking, we would recommend FAT3 topology based on InfiniBand adapters. And yeah, we have a lot of products that are being sold through a lot of vendors that you can put in your data center. If you want to address this problem, we have a dedicated product lineup that is focused on deep learning use case almost exclusively, and we're in every cloud. What I wanted to point out is the DGX1 lineup. So we have a product that you put underneath your desk for that phase stage. We have a product that goes into your data center, and we're also announced on GTC a beta of a cloud solution that will be available for testing in July. Our hardware doesn't only come with metal, but it also comes with a fully managed and optimized stack. So regardless which deep learning platform you're using, we will deliver it together with the hardware, and you'll get monthly updates, and you can rest assured that it will actually be performant. And to join us, if you want to learn more about use cases, see more fascinating applications, learn about technology, come to Munich for our European GPU conference. And thank you kindly. I'm open for questions. Oh, and this gentleman here, you, Mark. So do catch both of us if you have any questions.
Muchísimas gracias, Adam. Vamos a pasar a tomar el café dentro de la sala. Al fondo pueden tomar el café y los laterales. Agradecerles, y espero que haya sido interesante esta primera parte de la jornada, agradecerles que cumplimenten el cuestionario, como digo, y retomamos la jornada con 5 conferencias y una mesa redonda a las 11:45. Continuamos con la jornada. Gracias.
Thank you.
Thank you.